Thank you. So, firstly, I would like to thank the Professor Fenocho and the organizing committee for inviting me in this interesting meeting on quantum neuromorphic and unconventional computing. So I'm very happy to give a talk about this work on physical deep learning based on dynamical systems. So this work has been done with the lab member, Mr. Genki Furuhata and Professor Tomoaki Niyama in Kanazawa University in Japan. Okay, at first, to explain the motivation and the research background of this work, so let me start with the discussion on the neural computing hardware. So as you know, neural computing hardware has attracted recently much attention. So because such computing hardware can accelerate the neural processing based on the inherent advantage in terms of speed per consumption, latency, and scalability. And various substrategy has been proposed, ranging from photonics, spintronics, in-memory substrate to the chemical system. So those substrates are very attractive as computational resources to reduce the power consumption and increase the computing power. So now, so many researchers have tried to develop to develop the novel neural computing hardware. So also in our lab, so we are now trying to develop the unconventional neural computing. So let me briefly introduce recent achievement in our lab. The first one is the photonic neural-inspired computing. So with the photonic chip to generate a photonic field to used as a neural field. So which corresponding to the large-scale neural network. Actually, the photonic neural field can compute the once ahead of the value of the input data for the time series prediction task. And the advantage of this computing, so using the photonic technology, is to achieve the ultra fast computing. So over the 10 gigahertz and so on, so which correspond to the 1 petamark per second operation, which is much higher than the digital electronic computing. The second is the photonic chip to do the reinforcement learning. So especially for the much armed bandit problem. So this chip can find a best choice with maximal reward. So among the unknown choices. So utilizing the optical fluctuation. So as shown in those architectures, so we are interested in using a physical system, including a photonics, for novel computation. The next challenge is to physically make a deep neural network. As you know, the deep neural network is now a backbone of artificial intelligence. So depth of the network is very important to achieve high-level processing. So as discussed in those papers, as a theoretical consideration, so as the network is deeper and deeper, the network has higher expressive power to express the complex function. so that any shallow network can't express. So to achieve the higher level processing. So I think it is very important to incorporate the effect of deep structure for hardware implementation. Okay, so in this talk, so I will introduce a unified framework for using physical system as deep neural network. The proposed approach is based on the analogy to optimal control of dynamical system. And the approach can be applied to the arbitrary physical systems. So the approach is not limited to the photonic system. As a key example, I will demonstrate numerically so information processing using an optoelectric delay system. The benefit of the system is that the training can be done with only a few physical parameters. So unlike a standard neural network requiring a huge number of training parameters. So, and we believe that the approach can help to facilitate the hardware implementation. So the work has been already published in this paper. So if you are interested in this work, so please check it. Okay, so now, so let me discuss about deep neural network. So this figure shows a schematic of the neural network. The information is input to the input layer. So then the information is propagated from layer to layer. Important point is that the information is transformed in complex way. So due to the nonlinear transformation, so caused by the activation function and the linear weighted summation of the neuron at the previous layer. So if we regard the layer-to-layer propagation as a discrete time evolution, the transformation of the information transformation can be interpreted as a time evolution of the dynamical system. In this context, the input information corresponds to the initial state of the system, then the output corresponds to the end state of the system. Okay, so and the connection to the dynamical system picture is clearer for the case of the residual neural network called ResNet, so which is a network with a skip connection to achieve the deeper networks as shown in this figure. The ResNet equation described as follows. So H is the hyperparameter, U is the weight in the nth layer, and so F is the activation function, and R is the neural state at the nth layer. So as seen in this equation, so it is just the Euler approximation of differential equation. In other words, so we can easily imagine the continuous version of ResNet equation. So now it is called neural ordinary differential equation, so which has recently proposed in this paper. So now in this context, so we don't have any reason that so the concept of the equation and the application of the equation is limited to the standard neural network. In other words, we can apply the concept to the any dynamical systems. So in this context, so the R is interpreted as a system state, and U is not weight. So we can interpret U as a just control signal in this context. So then the training of the deep neural network corresponds to a kind of optimal control of the dynamical system. Okay, so to more clarify this point, so let me explain the difference in the neural network and dynamic system. So at first, the information is input and the transformed due to the feed-forward propagation to get the output. The loss function is computed from the information of the output, and the desired output is called target. Weight and bias parameters are trained, so due to the error back propagation, so to reduce the loss function. On the other hand, so the dynamical system, so the input information is encoded in the initial state. So then the state time evolved, so to get the output. So the dynamics is controlled so by the signal U, so to reduce the cost function, and then so output correspond to the desired output. So the question is, how can we train the signal U? So one method is the adjoint method. The goal of the method is to minimize the cost function, which is the function of the distance between the output and the target vector. At the first step, so feed-forward propagation is performed. So to get the output, then we can calculate the cost function. At the second step, the derivative value of the cost function is used to the error-like signal denoted by P, and the error signal is time evolved in backward. This process is like similar to the back propagation. And the error signal is used to update the signal U. And so these three steps are repeated so to minimize the cost function. So as you see here, that this method is quite similar with the method in this neural network. Okay, so in order to investigate the effectiveness of the adjoint method, so we did the numerical experiment using the toy model. So for a simple binary classification task with the spiral dataset, the goal of the classification task is to classify the input data points into the two categories labeled by 0 or 1. Applying the adjoint method to the model, so we can train the model for the classification. So this is the result for the classification accuracy versus the epoch. So epoch means the number of the training. So as you see here, so over the 100 epochs, so the accuracy approaches the 100%. So we can succeed in the exact classification for this simple task. The next question is, how does a dynamical system process information? So to visualize the information dynamics in the trained model. So we show the animation of the time evolution of the distribution. As you see here, the initial distribution is this entangle and become linearly separable at this moment and at the end time t to aid the classification. So linear separable. And the initial problem is a non-linear classification problem, but after the transformation, so problem is converted to the linear separable problem, so which is easy to solve. The conversion from the nonlinear problem to the linear problem is the fundamental mechanism for the information processing using a dynamical system. The transformation to linear separable distributions are quite general, and we can confirm the similar property for the different data sets such as square, donors, and so on. So this figure shows the effect of the end time t, which is a hyperparameter corresponding to the number of layers. So as the same case as the deep neural network, the accuracy improved as the deeps or the end time is increased. So we succeeded 100% classification for the this simple classification problem. Okay, so next, so let me discuss about what dynamical systems are useful for deep learning, deep neural network. So one solution is to use higher dimensional nonlinear systems, such as a coupled oscillator and nonlinear wave system and so on. However, so high dimensional systems require a large number of control signals. So because we have to control many degrees of freedom in the system. So it is very difficult to prepare the large number of control signals. So in context of the practical hardware implementation. Okay, so to overcome this problem, so we propose to use a delay system, so which is governed by this equation. So according to these theoretical papers, introducing the delayed feedback makes system high dimensional by introducing the delayed feedback coupling, and interestingly, many degrees of freedom caused by the delayed feedback act as virtual node. So in delayed feedback loop. So now, complex dynamics act as the virtual network dynamics. So in this case, so this system physically has a physical single node, but virtually high dimensional network can be constructed using the delayed feedback coupling. We use this idea, and so let me briefly mention the virtual network in delay system. Now, so time is discretized with the delta t with a time step and the delay time tau. So in the discretized picture, so the system state is described as follows. So which can be expressed as the jth neuron in the nth layer. So now the random trip corresponds to the layer, and the layer to layer propagation of the information is caused by the delayed feedback coupling in this case. So it is very easy to implement the idea for using the virtual network for the real hardware implementation. So to demonstrate the idea, so we use the optoelectric delay system, so which consists of the laser, intensity modulator, delay line, for detector, filter, and so on. So the signal is just objective laser intensity, and the nonlinearity is introduced by the intensity modulator. And so the optical fiber is used for constructing the delay line. And the control signals are used to control the amplitude and the phase modulation. Okay, this is an equation to describe that system. Okay, so for the demonstration, we use the MNIST handwritten text recognition task. At first, the input image is converted to the time series data. So then the time series data is input to the system. And after the third wraps, the transformed signals is extracted, then so sent to the softmax classification layer. So interestingly, the processing, so weighted summation are performed also in time domain. So using the time division multiplexing technique used based on the integrator and the multiplier and so on. Okay, so this is a numerical result for the MNIST recognition task. So this figure shows the classification accuracy, process epoch. As you see here, that the classification accuracy is about 97%. The performance is so, but what I want to emphasize is that the number of the parameters used in this study is much smaller than this standard neural networks, so which requires a huge number of training parameters, so over so close to the millions. However, the optoelectric system has only 22 parameters to be trained, but it is almost the same similar performance can be achieved. Okay. So, okay, this is a summary of my talk. So I introduced the framework for using a physical system as deep neural network. I introduced the concept, and I introduced the numerical result. So for the information processing using a simple optoelectric delay system, so which is capable of tackling the computationally hard task with only a few control parameters. So important point is the framework is platform independent. So this framework approach can be applied to photonic, spectronic, electronic system, and so on, I think. Okay, that's all. Thank you for your attention.